Okay, so let us next continue with these from exercise 17 through 30. So the 17th one is this limit solution x minus 5 over x squared minus 25. Now the denominator can of course be factorized like this. And we know that since x is approaching 5 and is hence not equal to 5, so x minus 5 is not equal to 0. So these two x minus 5's get cancelled out and we are left with this. One over x plus 5, which by the quotient rule equals 1 over the limit of x plus 5, and the limit of x plus 5 as x approaches 5 is 10, which is not equal to 0, and in fact that's why we are able to apply the quotient rule here. So that means the answer is 1 over 10. Next, here the independent variable x is approaching minus 3 and the function whose limit we are calculating is again this, just like that one. It's also a rational function, a quotient of two polynomials. The numerator is x plus 3 and the denominator is x squared plus 4x plus 3. So in this type of problems where the function is a rational function, usually what happens is that if you have x approaching a in your limit, then you will somehow encounter x minus a in the numerator as well as in the denominator, and these will then get cancelled, plus there are something, and then you evaluate the limit by substitution, that is by using the several limit laws. That is also the case here. In this case, x minus a is x plus 3 because a is minus 3. So let's see how we can, we already have x plus 3 in the numerator, so we should also get it in the denominator. That means this quadratic polynomial has to be factorized, one factor of which will be x plus 3. X plus 3 over x squared plus 4x plus 3. It's not very difficult to see that the denominator is just x plus 3 times x plus 1, because if you perform the multiplication, what will you have? X squared plus 3x plus x, that means 4x plus 3. Okay, so this equals, again, because x plus 3 is not equal to 0, so you can cancel it out from the numerator and denominator. And that will leave you with one over x plus 1. So just like before, we can actually simply substitute minus 3 for x. So that gives us minus 2 in the denominator. So finally the answer is minus 1 over 2. Then 19. The 19th one is this: limit as x approaches minus 5 of x square plus 3x minus 10 divided by x plus 5. So here the quadratic polynomial is in the numerator. Does not matter, that is the one we have to factorize, so that we get x plus 5 in the numerator as well. Okay, how can you quite quickly write something like this? You know that this type of problems that we encounter in textbooks are actually cherry-picked for us to show how a method works and to give us practice in something. Usually when we encounter something absolutely arbitrary in mathematics in general, then such nice situations may not occur. In fact, in most of the cases, nothing nice actually occurs. Only sometimes we get lucky and we see a pattern, and that helps us. However, because these things have been cherry-picked for us, so you can guess the other factor by looking at this constant term. You know that you are supposed to get x plus 5 in the numerator. So you just blindly write x plus 5. That is supposed to be one factor. But then what is it that you need here so that you get minus 10? Obviously you should write minus 2, because 5 times minus 2 will give you minus 10. And then you see whether this really becomes this. Let's see. X times x is x square, 5 times x is 5x, minus 2 times x is minus 2x, 5x minus 2x is 3x, and 5 times minus 2 is minus 10. So that way you can get the factorization pretty quickly. It is in fact, what can I say? Of course, we should see these nice problems so that we know how our methods work. But if we see only this type of things all the time, then we may get the wrong impression that this is how mathematics looks. Mathematics doesn't look like this. A general situation in mathematics looks very ugly. Okay, things will go up to some point, and then you may not be able to progress from there. You then have to follow another path to something else. That's how real mathematics works. These are of course also mathematics, but here only the nice things are being shown. Okay, that should always be kept in mind. So what I am saying is that these things will give us nice practice in handling these nice situations, but we should also be at least aware of the fact that these are nice, but many more things are not nice at all in mathematics. So here you can just simply substitute minus 5 for x, so that will give you minus 7. So that's the answer. 20. Here the independent variable is approaching to x square minus 7x plus 10 over x minus 2. Okay, now whatever I was saying here, can we do that here now? That quickly. We know that we should get x minus 2 in the numerator, but now we need plus 10. So let me write x minus 5, because according to what we were doing here, we should write x minus 5 here. But you should then see if that is correct, that's the correct one. X square minus 2x minus 5x, they give us minus 7x, and minus 2 times minus 5 is 10. Yes. Again, because x is only approaching 2, it's not equal to 2, so x minus 2 is non-zero, so you can cancel these two x minus 2's, and that leaves you with x minus 5. Substituting 2 for x, we get minus 3. There are some little things that should always be kept in mind. You see, if in your haste, because you have understood how to solve the problem, in your excitement and haste, you may forget to use these parentheses and write something like this carelessly. Although we know and we understand from how the process is going that this is the limit of x minus 5 as x approaches 2, but strictly speaking, it can also be understood as the limit of x as x approaches 2, that is this minus 5. You would say that that is not a problem. Actually, it's not a problem. If someone misinterprets this thing like this, then also one would get minus 3, but that may not be always the case. If you forget this kind of things, then you may end up making mistakes. So it's better to use parenthesis brackets wherever they are needed. Next, 21. Limit t tends to 1, t square plus t minus 2 over t square minus 1. Now here both the numerator and denominator are quadratic polynomials, but we of course know what the thing that we what the thing is that we need to cancel. It is t minus 1 because t is approaching 1, and t minus 1 you can immediately see it is there in the denominator, but then you have to bring it in the numerator as well. Okay, so we carry out the factorization in the denominator first because that's the easier one. T minus 1 times t plus 1, and this is the problematic factor. So we write the problematic factor in the numerator as well, and we need minus 2. So if I write t plus 2, then minus 1 times 2 would give me minus 2. But what about the other things? T square, of course, we will get, no problem. But 2t minus t is t. Yes, so we are having the correct thing. So after the cancellation, we have t plus 2 over t plus 1. But now we can just use our quotient rule, because the limit of the denominator is not 0. In fact, it is 2. And the limit of the numerator is 1 plus 2, 3. So that means the answer is 3 over 2, or 1.5. Next, 22. Here the independent variable t is approaching minus 1, and the numerator polynomial is t squared plus 3t plus 2, and the denominator is t squared minus t minus 2. Okay, so here it's not that obvious how the factorization should go, but let's see. At least we know that we should search for what should be the problematic factor here. Since it is minus 1, the problematic factor will be t plus 1. So again, believing that the problem has been cherry picked and there should be no problem in having t plus 1 here as well as here. So we write t plus 1 in the numerator as well as in the denominator, and then adjust things. T squared plus 3t plus 2 over t squared minus t minus 2. Okay, what is it? T plus 1. And you can clearly see that the other factor should be t plus 2, because 2t plus t will give you 3t, 2 times 1 is 2, and t times t is t squared. But here, what is it that we should have? Since we have plus 1 here, we would need minus 2 in order to get minus 2. So let's write t minus 2 and then see if we are getting the thing correctly. Minus 2t plus t is minus t. Yes. So after cancelling the common factor, we have t plus 2 over t minus 2, and then by the quotient rule, the numerator becomes what? 1, and the denominator becomes minus 3. That means the answer is minus 1 over 3. Next, 23. Here, okay, we have gone back to x. X is approaching minus 2, and the numerator, okay. The numerator is this linear polynomial minus 2x minus 4, and the denominator is this cubic polynomial x cubed plus 2x squared. No problem, we just have to see that we get x plus 2 in both the places. Minus 2x minus 4 over x cubed plus 2x squared Okay, so the factor that we are seeking is x plus 2. Well, you can clearly see that if you take minus 2 common out in the numerator, then you are left with x plus 2. And in the denominator, that you will get if you take x square common out. So after cancellation, you have minus 2 over x square. The numerator is constant, so it will stay minus 2, and the denominator upon substitution will be 4. That means the limit is minus 1 over 2. Next, 24. Okay, here the independent variable has been chosen to be y, and y is approaching 0, and the function is 5y cubed plus 8y square over 3y to the power 4 minus 16y square. So in this case, the problematic factor is actually y. Y minus 0 is y. And we can get rid of y. In fact, we can get rid of y square because that appears in the numerator as well as in the denominator throughout. Like this. Five y plus 8, 3y square minus 16. And this will become what? The numerator will become 8 and the denominator will become minus 16. That means the answer is minus 1 over 2. Next, 25. Limit u tends to 1, and the function is u to the power 4 minus 1 over u cube minus 1. Well, in this case, what is our factor that we need to cancel? U minus 1, and that you can see will come easily in both the numerator and denominator from the formulas that we already know of factorizing such things. For example, this u cube minus 1 can be replaced with u minus 1 times u square plus u plus 1. This is a formula that we already know. Okay. And what about the numerator? It can be factorized, and actually it will happen 2 times. Once you would write u square plus 1. Okay, let me write that. Times u square minus 1, but that u square minus 1 itself can be written as u plus 1 times u minus 1. So now after cancelling the common u minus 1, you are left with u square plus 1 times u plus 1 over u square plus u plus 1. And now what is the value of this limit? The numerator becomes what? 2 times 2, that is 4, and the denominator becomes 3. Okay, so that is the value. Next, 26. Here the independent variable is v. Actually it does not matter what you call this independent variable. But I think the author is taking different names for this variable just to make it look a little less boring. You can work out all these problems with just the variable name x. Nothing will change. So here the function is v cube minus 8 over v to the power 4 minus 16. Okay, a similar factorization like this, again a cubic polynomial and a biquadratic one. So we have this is equal to okay, but let's just express it a little more clearly. I mean this second term, in place of 8 you can write 2 cube. Similarly here, in place of 16 you can write 2 to the power 4, and then you factorize. So here in the numerator the factorization will go like this: v cube minus 2 cube is v minus 2 times v square plus 2v, that means this times this, plus 2 square, that is 4, and in the denominator this is v square plus 2 square, that means 4, times v square minus 2 square, but that v square minus 2 square itself can be factorized as v plus 2 times v minus 2. Okay, now without being lazy, let's just destroy this pattern and continue the problem here on this side. Now after cancelling the common factor, we are left with v square plus 2v plus 4 over v square plus 4 times v plus 2. Now what will the limit be? For let me just first write what we will get if we substitute 2 for v. Okay, so what will it be? 12 in the numerator, and in the denominator 4 plus 4 is 8, 32. Okay, so that means we can do a little cancellation, right? We can cancel the common factor 4. So this is the answer. Oh, I forgot to write the number. This is 26. Then 27. Limit x is approaching 9. and square root of x minus 3 over x minus 9. Now when you see this kind of things, you should also, although you should not really care about these things when calculating the value of such limits, but you should still see what is going on here. I mean, what I'm trying to say here is that you should be able to at least see what type of x we are dealing with. You see square root of x, right? So naturally x cannot be negative, because then we would lose meaning. We are dealing with real numbers and real quantities here, not non-real complex numbers. So you can see just from the look of this function, you of course already know what its domain is, what its natural domain is, and that natural domain of course would lie on the real line, because x has to be non-negative, so it will lie on the right side of 0, including we can take x equal to 0, there is no problem, but we cannot take negative x. And we have here a 9 over here somewhere to the right of 0. X can take any non-negative real value, but x cannot take 9. So the natural domain of this function is this. So this is where all the x's are lying, and in this set we are making x, that is we are taking x and making it close to 9. That can of course be done in two ways. Either you can take x here in this portion of the domain and take it towards 9, or you can lie here. You can take x here and then make it approach 9 like this. Why I am saying this? That's because you should at least have an idea of what type of x we are dealing with. All these things should be in the back of your mind. I did not say anything about this here, because here the situation is quite simple. All the variables that we were considering were taking just real values, except at the point where you would have a 0 denominator. That value is not taken. That's why we were saying that v is, for example here, v is not equal to 2, but we can take any other real value. Here however, due to the presence of this square root, a little more restriction is needed. Sometimes this kind of considerations can become crucial. Okay, so let's just continue. Over x minus, you will now realize why I was saying all these things, because in the very next step square root of x minus 3. Now what we are going to do here is, in place of x we write this, and the knowledge that x is coming from here allows us to do so. If x had x been a negative real number, you cannot write like this. That is, what I am saying is that you cannot write something like this. You can write, of course, but that is in the domain of complex numbers, not in our discussion. Okay, for us all the things are real. X is real, and in fact x is real, but even more restricted. X cannot be just any real number, and the value of the function is also real. We are dealing only with functions that take real values as input and give back real values as output. That's why we have to consider these things. Okay, it is because of non-negativity of x that x is equal to square root of x, square root of x square. And now you can see that there is a possible factorization in the denominator. We won't write the reasons here explicitly, but the reasons are there in the background. Okay, now note carefully that because x is not equal to 9, so square root of x is not equal to 3, because had square root of x been equal to 3, x would have been equal to 9, but that's not the case, because x is only approaching 9, it's not equal to 9, and that's why these two things are non-zero. So you can cancel them and have this. Now you can substitute 9 for x. By what rule? By the power rule. You remember there is a power rule also. So that allows us to replace x with 9. That is, the limit will be this. But that is just 1 over 6. So you see that this one is, yes, it is like those things, again a quotient, but this is not a rational function because the numerator is not a polynomial. So it's a little bit more, I should not say it's difficult, but some other considerations are needed to handle it properly. Next, 28. Here x is approaching 4 and the function is 4x minus x square divided by 2 minus square root of x. This is also something similar, but we are not going to discuss that much like the previous one in this case, because now we know what is going on in the background. X minus x square over 2 minus square root of x. Okay, so here the problematic factor and the one that you need to cancel is this itself. Either you see, you can do two things. Either you bring 2 minus square root of x in the numerator, or somehow you modify the denominator itself so that you get x minus 4 in the denominator, and then you can also see that you would get x minus 4 in the numerator as well. So let's just do that. Okay. So for that, what we would have to do in the beginning itself, to make things a little bit easier to interpret, let us take x common out. So that leaves us with 4 minus x, but simultaneously we also multiply and divide by 2 plus root x. But again, while doing some things like this, you should make sure that whatever you are introducing here extra is non-zero. Is it possible for this expression to be 0? No, because the least value that square root of x can have is 0. But you add that with 2, so that means the smallest possible value of this 2 plus square root of x is 2. It cannot be 0. So this is justified. So this now becomes this, which again gives us four minus x. So that's how we have brought 4 minus x in the denominator, and we can now cancel it. After the cancellation, we are left with this. Okay, so now using the product rule and the power rule in combination, the value of the limit is this. That is, this should be equal to 4 times 2 plus square root of 4. So that would be 2 plus 2, again another 4, so 16. Next, 29. Limit as x tends to 1 of this function, x minus 1 divided by square root of x plus 3 minus 2. Here you know that your factor that you need to cancel is x minus 1. Already one x minus 1 is sitting in the numerator. So we need to bring x minus 1 in the denominator as well by doing something like this. That is, it has a name also, rationalizing the denominator. You already have come across this thing, rationalizing in the denominator, rationalizing the denominator, but there you did not have, you did not likely have x or such things, only some numbers. The square root of 2 plus square root of 3. It's that same thing here. Minus 2. So rationalizing the denominator demands that we multiply and divide by this square root of x plus 3 plus 2, and just like this one, this also cannot be 0. So that means this is justified, this step. Okay, so that would change the denominator. Okay, let us first write the numerator, and it would change the denominator to this. x plus 3 minus 4, which is x minus 1. And after cancellation, we have this 3 plus 2. Now using the power rule, the sum rule, all those things, we have this as the value of the limit. That means 4, square root of 4 is 2, 2 plus 2 is 4. And finally, number 30. Number 30 is again another one like this one. The independent variable is approaching -1 and the function is square root of x square plus 8 minus 3 over x plus 1. Okay, so to just make it a little bit more difficult, a quadratic polynomial has been taken inside the radical. Here, however, you had linear polynomial. Many people are put off even when starting these things by such exercises which look almost the same. It seems like solving these exercises is a wastage of time, and you feel that you will be able to handle such exercises even without solving them. That is, in effect, you start skipping many exercises. But the exercises, I mean, the more you solve this kind of things, even if a little dull, they are dull somewhat, admittedly, but they will teach you to do the right things in the right places. And the more you practice these things, the more you become accustomed to doing the right things. And at some stage, it will be so that you start doing the right things subconsciously, okay, even without you noticing. So that's why practice is very important, no matter how dull it looks. Okay, so let's handle this final one. So here we need to bring x plus 1 in the numerator. So again, here we need to, here we are not going to rationalize the denominator, because there is nothing irrational in the denominator. Nothing irrational means no irrational expression. X itself may take an irrational value, that's a different matter. But we have to rationalize the numerator itself by multiplying and dividing by this, which again, if you notice, cannot be 0, so there is no problem. Plus 3. Minus 3 square x plus 1 square root of x plus 8 plus 3 x square plus 8 minus 9. What? Oh, okay. Oh, so here Okay, what it looks a little off, this problem. If it is really this, then we are not getting x plus 1 in the numerator by doing this, no? Because we would get x square minus 1. So that does not solve the problem of having x plus 1 in the denominator. But it is most likely the case that I have made a mistake in taking down this problem from the text. So what I will do, I will leave it like this here, unsolved, and we will handle it in the next video, next calculus video, because I am not sure if I have been correct here in taking down the problem. Most likely I have made a mistake. But if it is not a mistake and this itself is the problem, then it's somewhat interesting, more interesting than these other things, because now we have a problem, how to go forward. So let me just stop here itself, and we will handle this in the next calculus update. So that's just it for tonight. Our next upload is this coming Friday, and on Friday let's go back to our vector spaces, where what are we doing right now? Oh, we are doing inner product spaces, right? So we will see what comes next. So see you on Friday with inner product spaces. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.